say a few words, a few things about the second one. Here we talk about the selection problem. Yeah. So we know the selection problem, find the kth smallest, right? Yeah. So the problem is find the kth smallest element in a given array. Okay, yeah. But k must be given, yeah. Could be any number from 1 through n. Right, yeah. Here, this question is designed to check if you know one important conclusion. Yeah, yeah. Because for this problem in our class, I didn't give you the solution. Yeah, the reason is the solution is pretty complicated. Yeah. So if I give you the complete solution, very difficult to understand. Yeah. So I skipped that part, but I gave you the conclusion. Yeah. So conclusion is given. So you only need to find the conclusion. Yeah. The conclusion is if there exists an algorithm in big O of n. Okay, yeah. Big O of n, or we can call a linear algorithm. If a linear algorithm exists for the selection problem. Yeah. So you only need to find that conclusion. Okay. So that is the second question. Yeah. Then after that, just some basic, properties. Yeah. But you need to know the details. Okay. Yeah. Here. So these two, you need to know the details. After we learned these sorting algorithms, you need to know the properties of these sorting algorithms. Yeah. Next one about the binary search, right? The binary search, here I like to check if you know the exact formulas for worst case efficiency. Yeah. Usually we know the overall efficiency. Usually, most of the time, what do you see? Things like this. Yeah. But this formula you can see when you have this big O notation, not very accurate, right? Yeah, big O, that's not a accurate or precise formula, right? So that's the asymptotic. That's the approximate formula. So this question, I ask you for the precise formula. Yeah, precise formula. Yeah. In our notes, we have the precise formula as actually we have two equivalent versions. And here I only ask you to give one of the two formulas. Yeah. So only one is correct. Yeah, I didn't put both. Yeah, but yeah, because I usually in my multiple choice questions, I only want to give you one correct answer. I don't want to confuse you, okay? So the two correct formulas, I only put one of them here. Yeah, the remaining three close, but not correct, okay? Not exact, okay? Yeah, so you need to find exact formulas from our notes. Yeah. All right, so that's this question. Number 6, I like to explain one term I didn't talk about in class. Yeah. Here the question, the heap data structure, which of the following types of binary trees? So here we need to look at the two different types, basically. One is the full binary tree, another is complete binary tree. These two types. Complete binary tree, so we know the structure, right? But for the full binary tree, some of you, many of you may not know it. Yeah, because I didn't talk about this concept in our class. So here, let me give you the concept. All right. First, they are different. Okay, full, complete, so they are different. Yeah. And the full meaning, yeah. So why we call it full in some sense, right? Yeah. So here we consider a typical node in this tree. Yeah. Consider one node, okay? Yeah. Anywhere in the tree, one node. All right. Each node, yeah, let me write in this way. The property, the main property of this type of binary trees, each node in a full binary tree has either 0 or 2 child nodes. That's the definition. Either 0 or 2, that means no one child node, one child node in it. Okay, that's the full binary tree. Full, okay, that's the full binary tree. No one child case. Okay, yeah. So you may like to understand why people think about, why people consider this type of binary trees, right? There must be a good reason. Must be a good reason. Yeah. Here, the reason to introduce this type of binary tree, so that is, we know there is a special technique. It's called a decision tree technique. Decision tree technique. So what's that? When you make a decision, we can draw binary tree, right? Decision tree. Yeah. When we make a decision, what kind of decision? For example, usually we compare A and B, two numbers, A and B. So that's a decision situation, right? Yeah. When we compare A and B, so usually we want to arrange the results using a binary tree. Yeah. So there are two cases one consider. Yeah. One case A less than or equal to B, and another one is A greater than B. So two possible cases. Okay. Then when we want to represent the algorithms based on comparisons like this, we can draw a decision tree here. Okay. And this decision tree, you can see it's a full binary tree. That is the full binary tree. And the decision tree method is very useful, very powerful. But in this class, I cannot find the time to talk about the decision tree. So here, I just give you a little background. Now, so remember I mentioned one important result. I gave that to you long time ago. Yeah, so here, let me talk about that. The, lower bound. Yeah, so I give you one important result before. So that is, what's that? Lower bound for sorting an element array. Lower bound, okay? An element array, the lower bound is ceiling function of log factorial. This lower bound, okay? Yeah. But that is the result. How to discover it? How to get this result? Now I can tell you using the decision tree technique, we can derive this lower bound result. Yeah. So here I just want to say this technique is very powerful. Otherwise, very hard. Yeah. Otherwise, how can you find this lower bound? Not easy. Okay. Yeah. All right. So now, after you have this background, then you can understand first, there is some big reason people introduce this concept for binary tree. Yeah. Then you just go back to our question here for a heap data structure. So do we use the full binary tree or, complete or near complete? Yeah, here I put a near full binary tree, yeah. We know near complete, so we do not require complete the whole tree. Yeah, but, we can change the condition slightly. Full, near full, yeah, we can change condition slightly, in a similar way. Yeah, yeah. All right, yeah. So that is the question number 6. All right. Then, right, yeah, some basic facts. So I do not need to explain. Yeah, leaf. Internal node, external, internal, leaf nodes. Yeah, I talk about in class. Yeah, so you just study that part. Yeah. Then checking max heap. You just examine the max heap property. Yeah, everywhere in this tree. Yeah, so that pretty straightforward. Yeah. And all right, so the remaining these things. Yeah. Number 12, here I ask you to run one quicksort partition. Yeah. I want you to know the details of quicksort partition. Yeah. And in class, I use one example. Yeah, one concrete example. So I use diagrams, I show you step by step. Yeah. I use different colors. Yeah. So you need to study those slides. Yeah. Understand the whole procedure. Yeah. So then after you understand, then you apply here. Just apply it once. All right. One partition. Here, we only need one partition. Okay. Yeah. Do not do the quick sort. The whole quick sort. We do not need to do the whole quick sort, just one partition. So that's good enough. Yeah. All right. Then this number 13, the merge sort. Yeah, here I like to explain a little bit. Yeah. 7 element array. It's an odd number. Odd number. Okay. Yeah. How many comparisons do we need for the best case? Yeah. So here, let me show you a simpler example. So here, let me show you n equals 5. How about that? Okay. Yeah. If I work on the question, but I just change n from 7 to 5. Yeah. So let me show you the typical way for this question. Yeah. Divide and conquer, right? Yeah. Divide and conquer. All right. So there are, here we have 5 elements here. Yeah. We try to split in the middle. Yeah. Try to make the elements in 2 different subarray as even as possible. Yeah. Here we have to make, one subarray, 3 elements, the other 2 elements. Okay. All right. Then divide another round. Yeah. So another. Yeah. Okay. Yeah. 2 and 1. All right. Yeah. Then the last round split. Yeah. 2. Yeah. 2. All right. Then we can start merging. Yeah. Start merging. Yeah. First merge. Yeah. Merge these 2. First round merging. Yeah. Okay. When we do the merge using the best case, remember we have 2 formulas, best case formula and the worst case formula. Yeah, here let me review a little bit. Okay, merge two subarrays. Yeah. With the first subarray with m element, the second subarray with n elements. Yeah. So we have formula, best case formula and the worst case formula. Yeah. So you need to read the question carefully. Here, we just need to apply the best case formula. Best case formula, that is the minimum of these 2 numbers, m and n. The worst case formula, that is m plus n minus 1. Okay, all right. So here we apply the best case formula, merge m equals 1, n equals 1. So the minimum is 1, right? Yeah. So one comparison, we can merge, for the best case. Here also, one comparison, we can merge these 2 subarrays for the best case. All right, so then the second, merge these 2. Okay, these 2, m equals 2, n equals 1. The minimum is 1, right? So another 1. All right, another 1. Okay, all right. The last round, merge these 2. One is 3, the other is 2. The minimum is 2, right? Yeah. Yeah. So then we get, so you add up all the comparisons, 3 times, right? 1 comparison 3 times, then plus 2 comparison. So the total is 5 comparison. How about that? For the best case, okay? So you get the answer for the best case. For this question, then you just apply n equals 7 using this way. Okay, the best case formula in this way. Yeah. But when you do the split, make sure you split in the right way. Yeah. In multiple rounds. Okay. Yeah. The bottom, starting from bottom level, merge. When you merge, basically you reverse your splitting procedure. Okay. Splitting, so you have certain way, right? So when you do the merge, just reverse your splitting process, the merging process. Yeah. So then you will get the correct answer. Okay. Yeah. Similarly, later, you may have the question, we may need to apply the worst case formula. Okay. Yeah. You just switch to the worst case. Yeah. So your answer will be different. Okay. Yeah. So that's this question. Yeah. All right. Then next question. Yeah. A heap with certain number. Here we can just assume n equals this number. Yeah. How many nodes are there in the heap of height 2? Yeah. First, you need to know the height concept, right? The height concept. Yeah. Yeah. We spend a lot of time study the height for different nodes in the heap. Yeah. And we have formulas. Yeah. We have, formulas. Yeah. So here I like you to, understand the structure based on the binary tree structure of a heap, connect to the heat information. Yeah. All right. First, for the height, yeah, suppose we have a, heap like this. All right. Ground level, right? Yeah. Here also, ground level like that. Ground level, the height equals 0, right? Yeah. Because, we use the ground, we define ground as the 0 height. Yeah. Then this one, height equals 1, and so on. But for this one, you may reach the ground this way and reach the ground that way, 2 different ways. Then we take the longest. So the height equals 2, not 1. Okay, yeah. So that's the basic meaning of height here. And here I like to draw a diagram to explain the property explicitly. Yeah. So then when you answer the question, you can use this property. Yeah. So suppose this is an array corresponds to a heap. Yeah. For the heap, yeah, the position number for the root node, that is 1. The position number for the last node in the heap is n. Okay, yeah. So then we divide this line segment into multiple subintervals. All right, yeah, all right. The first subinterval here Okay, yeah. This subinterval, yeah. So this point, the position number is +1. Okay, position number, yeah. All right. Then, including this point and the last point, this first subinterval corresponds to height equals 0. So that is the leaves. That is what our definition of leaves. Okay, all right. Then, next subinterval, this point, yeah, n/4 + 1. Okay, n/4 + 1. And here, because this point belongs to that leaf, so this one is the n/2 point, yeah, the second subinterval. This, all the nodes with position number in this interval, height equals to 1, and so on. All right, let me do another one, so then you can get an idea. All right, another one, subinterval n/8 + 1, but the last point in this subinterval is n/4. Okay, so this subinterval, height equals 2, and so on. All right, that's the structure, the basic structure, the height, okay, with the position numbers. Yeah. All right, so here, how many nodes are there in the heap of height 2? Yeah, height 2, here. Here, this question, I ask you, how many nodes in this subinterval? How about that? In this subinterval, yeah. We have the formula, yeah. So in the notes, you can find the formula, the number of nodes with a given height number. Yeah. So you have that formula. Yeah. So you can find that formula, you plug in, you can do the calculation directly. Here I draw this diagram, so give you the basic structure of a heap, and you can use this diagram to answer, many other questions. Yeah, because this is a basic structure. Yeah, basic structure. So later you can use this diagram to solve many problems. Okay, yeah. All right. So that is this question. Yeah. Number 15, yeah. So based on my experience, many students ask me to explain this question before. Yeah. Here, let me give you the meaning I want to ask you in this question. Yeah. M and N. M, the meaning, the minimum number of elements in a heap of height h. And the N, the maximum number elements, also height h. Okay, yeah. So what is the expression of m plus n in terms of h? Yeah. All right, yeah. So here I draw two diagrams for m and n situation. So then you know the answer immediately. Okay, for the m case, Yeah. So we know the height, and we want to draw a heap with the minimum number of nodes. So that is the M case. Yeah. So let me draw M case. Binary tree. Yeah. Let me draw a few, nodes. Yeah. Here. All right. Yeah. So here you can see I draw levels, but when I reach the last level, I only draw one node. I do not draw more than one. If I draw more than one, that's not a minimum, right? Yeah. So only one node in the bottom level for minimum. Okay. Yeah. If I put one more, then it won't be minimum, right? Minimum plus one, so that won't be minimum. Yeah. So this is the M case. Okay. All right. The N case, maximum. Then we should put the maximum at the bottom level, right? Yeah. Maximum at the bottom level. So now you can see, it's very easy. Yeah. So the bottom level, we should pack maximum number of nodes. So that's the N case. All right. Now, another question we also know, the height is H. Yeah. Here we see height of H. We just look at the height of the root. Yeah. Height of this whole heap, that means height of the root is H. Here also, height of this root is H. Okay, yeah. Then, can you represent M in terms of H? The first thing you need to do. Second thing you need to do, represent N in terms of H. Okay. Then you add these two expressions together, N plus N, and do some necessary simplification. That is your answer. Okay, so that's the meaning of this question. Okay, yeah. Number 15. Next one, max heap value correspond array indices from 1 to n. What is the smallest possible index for the minimum value of the heap? All right. Let us try to understand the question. What is the smallest possible index for the minimum value of the heap? All right, minimum value. So here we consider the location for the minimum in the heap. Yeah. What property this element must have? Yeah. So first we know the minimum. You cannot find any other element with smaller value than minimum, right? Yeah, it has the smallest possible value in the whole heap. Yeah, that's its first obvious property. Yeah. But now we want to connect this property to the max heap property. What is the max heap property? Yeah. The value of the parent node cannot be smaller than the value of any of its child node, right? That's the max heap property. The value of a parent node cannot have smaller value than any of its child node. The value of any of its child node. That's the max heap property. All right. Then we can say this minimum element must be a leaf, right? Must be a leaf node. Okay. Yeah. That's the conclusion. Yeah. Because if it's not a leaf node, it must have a child node, right? Yeah, left child, it must have a left child node. Yeah, right child, we don't know, but we know it must have a left child node. Okay, if it has a left child node, then based on the max heap property, the value of its left child node should be smaller than the current node, the value of this current node, then it cannot be the minimum. It cannot be the minimum. So we have a contradiction. So then we must have this property. Okay. Then with this property, then we can find the answer. So here we know this minimum node must be one of the leaves in this heap. Okay. Then we go back to this diagram. So that's what I say. This diagram is very useful. This diagram is very useful. Now we know, yeah, leaf, right? So that means that minimum must fall in this subinterval, right? Yeah. All right. Must fall in this subinterval. And our question, the smallest possible index. The smallest possible index. Now you get here, the smallest possible index in this subinterval. What's that? Okay, you need to find the smallest index in it. See? Yeah. So that's your answer. Smallest index in that range. That's the answer. All right. Yeah. So you can see that diagram is very useful. All right. Yeah. Okay. Yeah. So that's this question. Yeah. Then next question. Yeah. N equals 378. Position number from 1 through this number. And now we consider a node with position number 87. What is the height of this node? Okay. Now, can you use that diagram to answer this question? You can see, yeah, that diagram is so useful. Okay. Yeah. Because in the diagram, you can draw those sub-intervals, right? For different high number, you can draw those sub-intervals. Yeah. You can see after you draw those sub-intervals, this position number, which sub-interval does it fall into? Okay, yeah, look at that. There must be one sub-interval that contains this position number. Okay, yeah. So you just find that sub-interval. Okay, yeah. And we have the, the boundary of the sub-intervals. Those, floor function, those boundary numbers for different sub-intervals. Yeah. So you can find the answer of, yeah, number 17. Number 18, n equals 77. How many leaves are there with the longest path from the root? Yeah. Here the situation is like this. All right. For a typical heap, and let me just draw a few more nodes. Suppose this is a typical heap. All right. And here we consider we start from the root, then we draw paths from the root to one of its leaves. Okay, one of its leaves. You can see when we draw the path to these leaves, that's the longest path. These two are the longest path. Yeah. But not these. The paths to these leaves, not the longest. Okay, not the longest. Yeah. So here the question you can see for this question, we need to find the number of leaves corresponding to these leaf nodes, but not that part, not that kind of leaf nodes. So you need to figure out, how to find a simple formula, to calculate these shaded leaves in this diagram, the shaded leaves in this diagram. Okay, yeah. So that's the meaning of this question. Yeah. Number 19, yeah, the merge question, but this time I ask you to merge 3 ordered arrays with the sizes, these 3 sizes. How many comparisons do we need to get an ordered array containing all these elements for the best case? Best case, use, every time when you merge, use this formula. Yeah. Because when you merge, you have several ways to merge, right? Yeah. You have several ways to merge. Okay. Here, I ask you to find the way with the minimum number of comparisons. And let's put together question 20, another similar question. Oh, yeah. Similar question, size is different, but for the worst case. This time when you do merge, you need to use m, this formula, m plus n minus 1, this formula. Yeah. So these two questions, the main formula for each merge step is different. Yeah. Okay, yeah. So other than that, because only 3 arrays, you can try different ways to merge them. Different ways, you will get different answers. You only need to find the one with the smallest number of comparisons. Okay, yeah. And another one, I noticed there is another similar one. Yeah, number 24. Yeah, there's another similar one, but this time the number of ordered array 4. Yeah, 4 different sizes. Yeah. The more ordered arrays, the harder, right? Yeah. Yeah. Here also use the, worst case formula. Yeah. But the question is, for the 3 ordered arrays, yeah, the previous 2 examples, 3 ordered array, the different cases, not too many. Small number of different cases. So if you try, so relatively easy. Okay, yeah. But for this question, when you have 4 ordered arrays, that number of cases can grow, probably too many, right? So if you try all possible cases, probably too many cases, yeah. So here, probably you can consider an algorithm we learned before. One algorithm we learned before, that's called a greedy algorithm. Greedy algorithm. Yeah, here. Apply some greedy strategy here. So when you make your merge operations, you can reduce the number of cases. All right. For example, to be greedy, when you merge, so here, 10, 15, 22, 37. Okay, yeah. So that's the, starting point. When you determine, the first time you need to determine which 2 arrays you want to merge, right? Make your first decision. So you apply some greedy strategy. Yeah. What greedy strategy? Merge 2 subarray with the smallest sizes, 10 and 15. That's greedy strategy, right? Yeah. So what's the greedy strategy? Greedy strategy means you apply some minimum or maximum based criteria here. Here, our greedy strategy, we want to make the, two ordered arrays to be merged. They have the minimum sizes. That's the greedy strategy. Okay, all right. Now, after we merge these two using certain number of, you can calculate the number of comparisons. Yeah. But after we merge, the merged subarray will have 25 elements, right? Yeah, 10 plus 15, 25 elements. Okay. After that, now you have 3 ordered arrays. Right? Yeah. 3 ordered arrays. This time you apply the greedy strategy. Another time, merge 2 arrays with the minimum sizes, 22 and for 25, and you have 47 elements, right? Yeah. After that, you only have 2 arrays, then you merge the last time. So that's the greedy algorithm. Yeah. If you have, large number of ordered arrays, relatively large number of ordered arrays, yeah. So the greedy algorithm is a good consideration. Yeah. Here we cannot say the greedy algorithm gives you the best solution. Here we do not know that that's true or not. Because in general, the greedy algorithm may not give us the best solution. Yeah. Sometimes it gives us best solution, sometimes it does not. And here we don't know. If you want to show the greedy algorithms really give us the best solution, you need to prove it. Or someone needs to prove it. Okay? Yeah. Here, I don't know if I can prove it or not. Okay? Yeah. Yeah. So that's the information. Yeah. The greedy algorithm. You can try. Okay? Yeah. Merging 3-element array, then to prove, probably easier. Okay? Yeah. But for four ordered arrays, yeah, to prove it has the best solution, it may not be easy. Okay? Yeah. So here, I just give you, information. Yeah. Still, you need to do a lot of work. Okay. So if you want to find the best solution, you need to do a lot of work, but you only just try the best you can. Okay. Try the best you can to get the best answer, the minimum number of comparisons for these 3 questions. Yeah, 3 merge questions. Yeah. All right, so let me look at the other questions. Yeah. Yeah. Number 21. Yeah. Binary search. What? 25 element. Assume that, yeah, here, there is a big assumption here. Assume that a given key appears in the array and it is between the 9th element and the 19th element inclusive. How many comparisons we need for average case efficiency? Yeah. So let me explain this question. Let me draw the diagram. We know it's an ordered array. So we have all the elements ordered, and we can write the position number 1 from 1, 2, 3, right? 8, 9, 10, 18, 19, 20, 24, 25. Okay, all right. Now, based on the assumption, the key to be searched for must fall in the minimum, the maximum must fall into this range. Then you can see how many possibilities, right? That's all the possible cases. Okay, all right. Now you need to think about, for each element in this range, here we only consider the elements in this range. The element out of this range we do not consider. Okay, all right. So then for each element in this range, each element in this range, how many comparisons we need for the binary search? Right? Yeah. We have a certain number, right? For example, when key equals 9, number of comparisons. What's that? Okay. When k equals 10, the number of comparisons. Okay, and so on. The last one, when k equals 19, number of comparisons equals 1. All right. Then at the end, you take the average of all these numbers. That's your answer. Okay, all these cases. Okay. And you know all the comparison numbers. Okay, yeah. Just take the average. So you'll get the answer. All right, yeah. Number 22, yeah. So based on your understanding, yeah, of the quick sort, yeah, here I do not explain, yeah. Number 23, yes, it sounds familiar, right? So I create this question, sounds familiar. Actually, we practiced several similar questions before. Yeah. So here I give you another one because many students still couldn't get the main idea. So here I choose this one. So for those students to practice another time. Practice what? Practice the elimination method. because that's the, one of the most important methods we learned in this class. Yeah, so you need to have that kind of problem solving training, yeah, using elimination method. Given 6 elements, x1, x2 through x6, we would like to find its third smallest element, yeah, the median, yeah, left median, yeah. It is known that x1 and x6 are two extreme elements, max and min, but we do not know which one is max and which one is min. Okay, yeah. What is the minimum number of comparisons you need to find the median? Yeah. So here, can you apply the elimination method to reduce the array size, right? Yeah. So based on the given information, some of the elements you do not need to consider, yeah, put into consideration, yeah, because you have some good reason to eliminate them. Yeah. After that, your array size becomes smaller, then you look at the original median in the smaller array size array, to find that element, how many comparisons you need. Yeah. So that's the question number 23. Yeah. Then the last question. Oh, we're close to the end of this class. Yeah, let me talk about, I cannot spend too much time, only 4 minutes. Yeah, the last one. Yeah, so this is a little challenging for you. So you need to, so this one, you need to really, check your understanding of the max heap structure. Yeah. Here, I only give you 5 elements. So relatively small number, so it should not be too hard. Yeah, but still, you need to do quite some work. Yeah. Here, let me draw the basic structure a little bit. Yeah. Because with the 5 nodes, our heap becomes the structure like this. All right, we just need to fill in these 5 nodes with different possible numbers. Yeah, in 1, 2, 3, 4, 5. Yeah, let me just use the position A, B, C, D, E. All right, yeah, for discussion purpose. All right, yeah. And first thing we know, because here we need to consider max heap, right? In order for the max heap structure, the maximum number, 5 maximum number, 5 must be at the root, right? Yeah, so that's easy. So we try to fix easy things first. Yeah. Second, the minimum is 1. Where can we put the 1? The minimum by the max heap property. So yeah, so 1 here, yeah. So 1, the position 1 can go to C, right? Yeah, C is a leaf. C, D, and E. Because they are leaves, the minimum must be 1 of the leaves. Okay, so you can only consider 1 in CDE. Yeah. Then for each case, yeah, 1 in C case, for each case, so it's case 1, 1 in C, case 2, 1 in D, and case 3, 1 in E. Okay, yeah. Then you consider, remaining nodes following the max heap property. Okay, yeah. So that's, try to organize your thinking. Yeah. So a lot of work. Yeah. So you need to try based on this direction. Okay, this direction. The good thing is think about after you fix 1 and 5, the remaining 3 positions, only 3 positions, right? You can arrange the 3 numbers in 3 positions, try different ways. So that should not be too hard, right? Yeah, only 3 different places you need to, play around. Yeah. All right. Yeah. So that's the pretty much all the hints I can give you for this assignment. Yeah. I hope after I give you the hints, if you can understand my explanation, you can complete this assignment with some good result. Okay, yeah. All right, so let me stop here, and I posted this hint file, so you can use this hint file to help you, complete your homework assignment number 2. Okay, yeah. All right, so that's it.